Yes, I'm Jake Glass with C4ADS, which is a nonprofit based in Washington, D.C.
And I'm Max Whedon. As I said, this is my first time at OpenSky, but firstly, thank you all for still being here. I know it's a bit late now, but yeah, we've had a number of great presentations throughout the day, but yeah, so we appreciate both online and here, you still being with us. So yeah, moving on to, there we go, the agenda. Yeah, so first going to speak briefly about who we are, what we do, and then a quick background on Gnss Interference. Then we'll dive into our paper, so the data and the methodology that we used, as well as finally some results and even a brief demo. And then, yeah, concluding with some future possibilities based on our work and the surrounding literature.
So to kick it off, just a little bit of brief information on what our organization does and why we're interested in this kind of data and this kind of problem set. So we're a nonprofit based in Washington, D.C. That focuses on using publicly available information in order to investigate illicit networks. So that's transnational crime, that's pretty much anything that involves illicit activity crossing national boundaries. And so we do that through both public and private partnerships. And we're big on transparency and using publicly available data for impact. So working with journalists, working with investigators. And in the course of that, one of the things that we've done is developed a flight tracking tool of our own that leverages data from ADS-B exchange primarily. And so it makes the tough analytical task of writing SQL queries, which is tough for our analysts because we're tech enabled, but not everyone has software engineering expertise. Not everyone has complex data analysis expertise. So that means that we wanted a tool that integrates aircraft tracking data with public ownership data and images of aircraft, for example, and timelines of historical registration data. So what we did is built those all into one software tool. And we're working on developing additional capability for that, similar to what OpenSky is doing, similar to what all of you are doing. We're interested in taking the raw ADS-B data and adding on events that help analysts make sense of it. So instead of having to be trained and an expert in flight data in order to understand what's going on, when you're investigating wildlife trafficking and you're looking for a private jet that's allegedly carrying cheetahs out of Africa, flying to the Middle East, you can look at this search tool and you can answer pattern of life, pattern of activity questions very easily. So you don't have to search on a specific aircraft on a specific hour. You can answer an analytical question like aircraft, private jets flying from Africa to the Middle East within a certain time period, maybe with certain city pairs, with certain geographies. And so that's what we've been working on. And so this is an overview of some of the features that we've developed. This will be available for all of you, but I'll get to the interesting stuff, which is Gnss Interference, which is one of the features we've been building into the tool, because it's very easy to observe Gnss interference in ADS-B data. There are a number of hotspots of that globally, and Gnss interference is a growing problem. So I just want to scope the problem set a little bit, which is what GNSS is. GNSS is Global Navigation Satellite Systems, and there are a few different variations. Typically, we just refer to all of them under the umbrella of GPS because GPS was the first one, the Global Positioning System, which is operated by the US government. And there are a few others that have sprung up over the past several decades. So there's Galileo, GLONASS, Beidou. Each of these are respectively the European Union's, Russia's, and China's satellite navigation networks. You can see in the chart here that all of these networks tend to use similar bands. They're all within the L bands, which is line of sight, generally communication, and it's very, very low power, making it vulnerable to spoofing and to interference. Oftentimes, this is deliberate. We've seen instances where nation state actors will create this interference. And because the GPS power from the satellites are very far away, they're very low energy, you have to have an amplified receiver on the ground in order to get those signals because it's below the noise floor at around negative 125 decibels. And you can also see from this chart that there's a lot of crossover in the frequencies that these different satellite systems use. So for example, you can see in blue here, Galileo intersects with GPS in yellow on the L1 band, as well as on L5. E6 is also occupied in part by Beidou, China's navigation system. So if you were to do a little bit of jamming on one of these frequencies, you would be able to take out a number of different services. And quickly as well, it's very easy to do so. You can use a hack RF, which is around a $300 Euro piece of equipment, and that can have a fairly high transmission power. So I've always joked that if you put a hack RF like in a high altitude balloon and flew it over a major city, you could wreak a lot of havoc. Not making any recommendations at all because that's very illegal, but that would be a serious attack and it would be a serious problem for navigation systems on the ground. And there are open source libraries that allow you to generate spoofed GNSS signals. So you can upload your own constellation of fake satellites into the hack RF, and then it will broadcast fake frequencies that resemble an actual constellation and override what's really in the sky. So there's been a lot of research on state actors using GNSS interference for political gain. So C4ADS published Above Us Only Stars in 2019, which I didn't contribute to, but which is very interesting because it looks at AIS data where you can see ships that are being spoofed onto land, specifically to airports. And those ships were in the Black Sea when they were spoofed to land. And so you can see the area in which the ships were spoofed. Like there's a line basically where there were ships that were spoofed to land, and then a couple of kilometers away, ships that were not spoofed to land, meaning that you could localize the possible position of the transmitter, which isn't always possible with ADS-B. In this case, the interference was likely due to trips by Putin to the coast of the Black Sea, where he was staying at a residence known as Putin's Palace. And so those political trips that were publicly reported on coincided with these ships jumping to an airport and were likely counter-UAS measures for drones. The MIT Technology Review also reported in 2019 on crop circle patterns where vessels in Shanghai were being spoofed to an industrial area on land in the city. And it was a lot of different vessels that went to this one clustered place. So that's another example of where GNSS spoofing happens in the real world. So there's also been previous research, as Martin mentioned. It's been a popular subject at previous Open Sky sessions. Darabse and others talk about, a couple years ago, they published and spoke at Open Sky about detecting GPS jamming incidents in Open Sky data. They looked at some of the navigational quality indicators that are present in ADS-B data. And so that includes the NAC-P value. And they talked about some of the limitations of that, which were that not all of the Open Sky data has NAC-P values, and not every aircraft's ADS-B signals include those values. Liu and others talk about GNSS interference characterization and localization using Open Sky data as well. And so we wanted to build off of that research, but add in an extra dimension of data, which is AIS data. Another example of previous research on GNSS interference is in the Mediterranean. This is a report from Eurocontrol from a year or two ago, from 2021, actually. They flew an A320 over Cyprus, and they looked at where it was affected by interference and where it wasn't. And you can see that reflected in this map here. And I'll talk about that a little bit more in a bit. So when we were looking at alternative data sources to pair with ADS-B data in order to increase the granularity of our analysis, we found mobile device location data available from commercial providers is an option, but it's expensive and there are privacy concerns, and the integrity of the input data is not guaranteed because it just comes from mobile applications. There's also maritime transponder data, which is ultimately what we settled on. It's widely available from a number of commercial providers. There are also networks similar to Open Sky that are available that have this data. If you feed their network, if you get an AIS receiver, they will allow you to download it, but those are not as global as the commercial providers like Spire, which we have been using for our analysis. And then there are also stationary ground truth GNSS receivers, which are an interesting option here, as there are networks offered by some organizations like the International GNSS service, which allow you to download these files, typically for calibrating GPS devices for timing, for precision timing applications, but they can also be used to look for interference, changes in signal to noise ratio on those devices. And so the reason we wanted AIS in addition to ADS-B data is because we can look at ADS-B data quality indicators, but AIS allows us to move closer to being able to attribute the origin of the spoofing and or the interference and what devices exactly it's affecting in an area. So ADS-B, it's a little bit harder to say exactly where a spoofing or interference transmitter is located, because ADS-B is, you have aircraft at high altitude flying over an area. It could be anywhere within a very large radius if there are a lot of planes being interfered with, something that we see in the Mediterranean. And the idea is that if we have an additional source of data, not only will we be able to solve gaps where there are not very many aircraft flying over a specific area, but we'll also be able to potentially attribute the source of these events, because moving platforms will be affected and then not affected, as is the case with ships. And so some of the indicators that we looked at here include in ADS-B exchanges data and generally ADS-B, the navigational integrity category, which is an expression of the possible error in the navigation unit on the aircraft. And these are integer values, and there are set limits for what those values should be between in order to achieve the necessary separation for aircraft in any given airspace. There's NACP, which is the horizontal position accuracy. And there's also source integrity level. In AIS, we were looking at some other things, including communication sync state, which indicates whether an aircraft is or whether a ship is getting its position from an onboard GNSS unit, or whether it is communicating through a ground station, suggesting that it doesn't have its own onboard unit. There's also a RAIN flag, which refers to receiver autonomous integrity monitoring, that can tell us in theory whether a vessel is, whether it has enough satellites in order to make an accurate determination of its location, and whether it is able to exclude faulty satellites because it has enough good satellites. We also looked at speed and path anomalies by looking at ships or aircraft in both sources of data that jumped and traveled at an impossible speed. That often coincides with drops in the ADS-B quality indicators.
So now we're going to briefly look at the methodology that we employed in our own paper that we submitted. So after choosing our metrics, whether they be AIS or ADS-B, we do a number of binning due to just the size of the data, essentially. Do a number of binning, and then we do some temporal slicing. So instead of looking just at the entire data set over the long term, which would be the spatial binning, we'd look at singular hours within each of those bin hexes, which I'll talk about in a second. And then we also generate a number of signal flags so that we can have a binary value of 0 or 1, whether that was classed as anomalous for that particular metric or not. And then finally, to do more visualizations, we combine both AIS and ADS-B. We can aggregate flags above our flags. We could say that any of this category's flags are true. We have a category flag, which is then true. So kind of reduce the number of columns that we're dealing with. And we can also filter so that we only include consecutive events. So a single out of character event, that's generally just noise. So if we filter to only have a string of consecutive events, then that's much more likely to be a genuine interference event. So going more deeply into it, spatial binning, firstly, we use Uber's H3. It's hexagonal, as you can see in the image, and it's also hierarchical. So we can choose whichever particular resolution we want, depending on the granularity of the data that we want. So as I said, we have a huge amount of data. In the 2 months of data that we used, just the AIS data that is, that we used in this paper, it was over 5 billion rows. So we use resolution 2, you can see in the table here, which is fairly large scale, but we look globally. So this was what we used for the purpose of the paper. And again, there are other alternatives out there. There's S2 as a geohash algorithm. However, we wanted the more circular generally, so that we don't have the more rectangular S2, and generally just it seems a very efficient one that we've used in the past, and yeah, it does job very well. So moving on to the hourly binning then, in that, as I said before, we're not just looking at the long term, we're looking at everything relative to that particular hour of the day and that particular hexagon. So instead of just binning by hexagon, we're binning by hexagon and the hour of the day. So this record on a random date at 9:31 would be binned into that particular hexagon from all the 9 to 10 AMs. So we would build a distribution of each of our signal metrics, and then we can actually generate these flags to classify whether that particular value is anomalous or not based on its historical distribution. So we have our metrics, we have things to do like com-sync state, and then bad NACP values, which is just a simple filter on NACP. And then we have the AIS and ADSB jumps, both for total number of pings as well as individual vessels or aircraft. And we combine them, so all possible combinations of the qualifiers. So we can say, okay, all com-sync state pings above the median plus 2 standard deviations, that would class that as anomalous for that particular flag. So we can have a number of flags like this as a way to try and quantify the different activity that's happening. But most importantly, it's just relative to its own hour of the day and hexagon. So following on from that, as I briefly mentioned, we can have a flag for that particular category. So barring the median, because that's generally not so much of a noteworthy flag that it's above the median, but we could say any CSS flag, any com-sync state flag, if any of those relevant flags are true, then we could say, okay, any CSS flag is true. And likewise with all the other categories. So what this allows us to do is not necessarily be a detection model in itself, but just to look at the relationships between the different metrics. So we have any com-sync state flag as an example here. So for all the hexagon hourly sliced records, we have what, 630,000 rows, but then we have the average values of all of the other aggregated categories flags. And then we can say, okay, for all of the hourly hexagons, which have com-sync state 1, we have less rows, but we have far more average value of the NACP events, as well as AIS jumps. Less so for ADSB, but we can see there that there is some relationship there. It's not the most watertight statistical test, but it's just analysis of the relationship between the different values. So taking this further, to graph this, slightly confusing at first sight, but we can see the relative increase in each of the different categories values, given that that particular event is true. So for example, the table we just saw, that would be this second bar or set of bars here, the com-sync state event. We can see that it's over 100% increase in the NACP filters that we did, as well as AIS jumps, and less so the ADSB jumps. So we can see, very broadly here that we have genuine positive relationships between these different metrics. So again, this isn't as a detection methodology in itself. This is more just to see whether metrics such as a com-sync state, which are less understood, could be genuinely useful to add as a purpose for data availability and other metrics to feed into detection models. So here we can see that com-sync state does seem to have some genuine utility in being a proxy to other more widely understood values, such as NACPs. So yeah, there are a number of assumptions and limitations in this work. So for example, when we build each of the hourly distributions, what we're doing is we're building the distribution and then analyzing that same period of data to detect unusual events in the data that we've used to build the distribution. So in many ways, it would make more sense to split that into in-sample and out-of-sample, or even some rolling walk-forward analysis there, so they don't have this look-ahead bias. We also assume when we build these distributions that what we're building on isn't anomalous in the first place. We assume we're building on perfectly normal data, whereas obviously there would be a lot of skew in that distribution if there's a significant amount of anomalous activity going on in the distribution that we built. So further to that, if a place was constantly anomalous for that particular hour of the day, that particular hexagon, then we would detect nothing at all, because it would be a completely normal distribution. And equally, the aggregate metrics I just discussed in the previous graph, so they don't really account for the difference in coverage between the AIS and ADSB, because there are areas of very low AIS traffic because it's landlocked that will never have a flag true for an area which has an ADSB flag as true, and vice versa. So there are certainly things to improve, but as I said, it is a way to test the basic relationship between the variables and whether it has some utility. So now, I should leave it. Oh, this is a video. There we go. So I'm going to hand over to Jake to do the demo, and then we wrap up.
Yeah, very quickly. So back to the Eurocontrol research that we referenced that shows a mapping of flight tracks that are affected by Gnss interference over the Mediterranean. We were able to very easily replicate this, and we were able to show the relationship between the ADSB quality indicators and the com-sync state indicator as a metric for detecting similar interference in AIS. And we were able to do that in these same areas. So you can see here, we're looking in Kepler, which is a mapping tool, and looking at currently this right here is the ADS-B data that shows us that there is over 50% anomalous points, and by anomalous, we mean with a, I think in this case, it's a NIC value, or the navigational integrity category, of 7 or of less than 7, which indicates that the aircraft has unacceptable uncertainty about its location. And you can see that this starts to fade. And then there are some interesting hotspots, for example, off the coast of Italy. But generally, areas in which you would expect to have more interference per previous research do show that in the ADS-B exchange data. This is a chunk from about a day. When we switch over to AIS, we find similar trends. So we'll switch over there in a minute, but also looking at Ankara, there are little areas right by the airport where there is more interference. That could be because aircraft are coming down to a lower altitude and they're ground-based interference devices. And then we'll switch over to AIS here, and you can see a very similar pattern. So we also see the interference around Libya, though it's more concentrated. So we don't see it as widely spread out. Instead, there are specific little blips where there are darker areas, which indicates a higher rate of COM-sync state where vessels reported that they were not getting their location from their onboard GPS units. And you can see also that area around Naples, where we saw in the ADS-B data there was an issue. There's the same thing present in AIS data per the COM-sync state flag. We also looked into the RAIM flag as an example of this as a possible metric in AIS, but the RAIM flag seems to change too rapidly that there wasn't a strong correlation with other quality indicators that might indicate GNSS interference. There are a lot of future opportunities for us here, including literally taking like a Kerberos SDR, like the previous speaker talked about, or a Kraken SDR, and looking for the sources of these interference. Also calculating the probability and the potential locations of different interference sources on the ground, especially once you bring in multiple sources of data. It becomes easier because you're looking at moving vessels on different altitude levels, both at like 30,000 feet and on ground level. And ground level is then affected by elevation maps as far as the radio signal could propagate. And machine learning is also a huge possibility here. Thank you very much for listening to us. I'll be happy to open it up to questions right now.